Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals. And in this class we are going to make use of the famous Leibniz integral rule to solve this problem. So here we are given a function f which is from the set of real numbers to the set of real numbers, and the function f of x is defined by this equation, that is square of f of x is equal to pi square plus the integral from 0 to x f of t dt, and f of x is not equal to 0 for all x belonging to the set of real numbers. And we have to find out the value of f of x, right? So let us make use of the concept of Leibniz integral rule to get f of x. So let us quickly see the Leibniz integral rule. So now let us consider an integral where the lower limit is a constant, right? Suppose here we have a and the upper limit is some function of x. Let us say the upper limit is u of x, and here we have f of t dt, right? So if we wish to differentiate this integral with respect to x, then Leibniz rule says that we have here f of u of x. So first we'll replace this t by u of x, and then we multiply this term with the derivative of u of x. That is, we'll write d by dx of u of x, right? So here we are considering a special case of Leibniz integral rule where we have to differentiate this integral where the integrand is f of t, and here we have dt, and the lower limit is a constant, right? So here we are taking the lower limit as a, which is a constant whose derivative is 0, and here the upper limit we are considering a function of x, that is a u of x, right? So the derivative of this integral is given by f of u of x multiplied with the derivative of u of x. So first we'll replace this t by u of x, and then we multiply this term with the derivative of u of x. So let us make use of this result to differentiate this equation. So let us take the derivative of both sides of this equation, and let us call this equation as equation number 1. So we have d by dx of f of x square, and here the derivative of pi square is equal to 0, which we will write in the next step. And then we have d by dx of the integral 0 to x f of t and dt, right? So here the derivative of pi square is 0 because pi square is a constant. The derivative of f of x square is given by 2 times f of x by using this result, that is d by dx of x raised to n is given by nx n minus 1, and then by chain rule we'll write the derivative of f of x, right? And here now we have to differentiate this integral with respect to x. So we'll compare this integral with this one. So the value of a is 0, and here we have the upper limit as a function of x, and the lower limit is a constant, so a is 0, and a u of x is given by simply x, right? So we'll differentiate this integral with the help of this rule. So now we can write f of u of x is x, and then we have the derivative of u of x, that is x. right? So now we can write 2 times f of x, and here we have f prime of x. D by dx of f of x is f prime of x, and here we have simply f of x, because the derivative of x with respect to x is 1. And let us call this equation as equation number 2. So now here we have a differential equation, right? So let us take this f of x in the left hand side. So we have 2 f of x, f prime of x minus f of x is equal to 0. And taking f of x common, we have 2 times f prime of x minus 1 is equal to 0. So now we have here two factors. The first one is f of x, and the other one is 2 times f prime of x minus 1, and the product is equal to 0, right? So we must have f of x is equal to 0, and 2 times f prime of x minus 1 is equal to 0. But here we are given that f of x cannot be equal to 0, so we'll discard this equation, right? And we'll take up this one. So we have 2 times f prime of x is equal to 1. So let us solve this differential equation. We have f prime of x is equal to 1 over 2. So now we can write this equation as df over dx. For f of x, we are taking the notation simply f, and here we have half. So we can write df is equal to dx, and here we have half, and integrating both sides, we have half, and here we have integral dx, and c is the constant of integration. Now the integral df is simply f, and here we have half x. Integral dx is simply x, and c is the constant of integration, right? So now again writing f of x for f. So we have the function f of x is equal to half x plus c, right? And now we need to find out the value of this constant of integration c by using some boundary condition. So now to get the boundary condition, let us substitute x is equal to 0 in equation number 1. So we'll have here f of 0, and this is f of 0 square, and here we have simply a pi square, and here we have 0 to 0, because here we are taking x is equal to 0, and here we have f of t dt. Now this term is equal to 0, because both the limits of integration are 0. So we are left with only f of 0 square is equal to pi square. Now taking the square root on both the sides, we have square root of pi square, and here we have the square root of f of 0 square. So we have now f of 0, and here square and this square root get cancelled, and we are left with only f of 0 is equal to plus minus pi, right? So when x is equal to 0, we have f of 0 is equal to plus minus pi. Now let us take x is equal to 0 in this equation. So we have f of 0, and here we have half times 0 plus c. This term is 0, so we have f of 0 is equal to c. Now f of 0 is equal to plus minus pi when x is equal to 0. So we have c is equal to plus minus pi, right? So this is the value of the constant of integration, that is c. So let us resubstitute it in this equation. So we have now the value of f of x is equal to half times x plus minus pi. right? So this is the required function, that is f of x, which is half x plus minus pi. So, viewers, this is how by the application of this rule, which is the modified form of Leibniz integral rule, we can solve these kind of problems very easily.